Alright, so hello everyone. In today's video, we're going to be covering one of the most essential topics for Bronze, and that is going to be complete search. And alongside that, we're also going to be using the problem triangles as an example. So to begin with, what is complete search? So complete search, as the name suggests, complete search searches through all possible combinations or through the complete set of possibilities. That's like hence the name. So it's super simple, but is used in at least like half or three-fourths of the Bronze problems, and is an essential algorithm to know. And a lot of the other algorithms that you'd use in Bronze also kind of stem off of it, kind of like the greedy solution, which we'll cover in a different video. So with complete search, an example would be, say I have to find all possible combinations of the first 10 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that add up to a certain number, let's say 13, okay? So one way you could do that is through a non-complete search way, which would be maybe like subtracting all values from there, 13 minus 1, 13 minus 2, 13 minus 3, etc., right? And then kind of we have those pairs, so it'd be 12, and is that between the 1 to 10? No. 11, no. 13, oh yay, 10, right? And then we have this as one pair. Maybe we could sort in a set. And for this problem, that algorithm was pretty easy to find, right? But not all problems are going to be that easy, especially in Bronze, which is why we want to learn complete search. In Bronze, lots of the time complexities, for example, like n is less than or equal to 10 to the 5, right? You'll see something like that, right? In all these complete search problems, and we'll also see this in triangles, these are normally pretty small because you're going to have like O to the n squared solutions normally. So for example, it's going to be like 1 10 to the 3, right? Because that's going to 10 to the 3 squared is just going to end up as 10 to the 6th. 10 to the 6th is less than 10 to the 8th, so we're fine, and it's going to go in time. However, 10 to the 5th is probably not going to be complete search because that's going to be 10 to the 10th when we square it and not in time. Okay? So we've seen that this is one in like a faster way to do it, but it's a harder algorithm to come up with. So say you wanted to think of like a simple algorithm, what would that be? And it's, as the name suggests, really simple. It's a complete search algorithm. Okay? So the way that complete search algorithm is going to be is we're going to have two for loops, okay? So for 1 to 10, and another one for 1 to 10. And in this first for loop, we'll call the variable a, and then the second for loop, we'll call the variable b, okay? Then if a plus b equals 13, that's a combination. We could just add it to the set, okay? And it's a lot faster way. However, this is going to take 100 iterations, whereas the last one we did, it only takes about, well, 13 or 12, right? So this is slower, but it's such a small value, 10, that it doesn't matter, right? 10 squared is 100. 100 is like nothing for this computer. And also, it's really simple to think of, right? Then we just add this pair. See? Just add every single pair that we find. And that's pretty much it for a complete search algorithm, and we'll see more about it in the problem we do. So the problem we're going to be doing is from the USACO 2020 February Bronze Contest, and it's called Triangles, Problem 1. So Problem 1 is normally one of the easier problems in USACO contests, and Triangles is part of that as well. It's a really easy problem, and it's only made super easy once you figure out how to do complete search. Okay, so pause the video and read through the problem, kind of think of your own algorithm, and try and solve the problem by yourself before coming back. All right, welcome back. And now what we're going to be doing is we're just going to be going over some of the important things, and I'm going to be pointing out some details that can help you like recognize it's a complete search problem, and then we'll think of an algorithm and solve it. And remember, since this is complete search, the algorithm is probably going to be really easy. So Farmer John's going to make a triangle pasture, right? So triangle is something we need to uh, pay attention to. A triangle has how many points? 3 points, okay? and there are n fence posts. 3 is less than or equal to n is less than or equal to 100. So since we see that n is at most 100, we can pretty safely assume that it's going to be a complete search problem since we're not going to go out of time limit, okay? And sometimes this number is also smaller and stuff, and you might be thinking, oh, I can have like 8 for loops or something. But pause, okay? 8 for loops must mean that the solution you come up with is pretty complex. But we know that complete search is generally pretty simple, right? Maybe 2 or 3 for loops is fine, 4 maybe, but 8 for loops? That's probably a little too much, right? So remember that just because it's a small value doesn't mean you can like make as many for loops as you want. You still have to be kind of in like a reasonable amount. And remember, these bronze problems are generally pretty simple and you can probably get them within like 30 to 50 lines of code. 8 for loops is definitely not there. That's like just writing the loops itself takes about 16 lines of code and it's not going to be the solution. Okay, carrying on. At distinct points, okay, on a 2D map of this farm. Okay, so it's 2D. He chooses 3 of them to form the vertices of the triangle pasture, and one of the sides has to be parallel to x-axis, okay, and another side is parallel to the y-axis. And we need to find the maximum area, okay? So we're seeing that we're getting a bunch of points, and we just need to check whichever ones kind of match this x-axis and y-axis criteria, and then we just kind of find the area and double that, okay? So if you don't know already, the area of a triangle is going to be 1/2 base times height. And we can see that that side that's parallel to the x-axis is probably the base, and the side parallel to the y-axis is probably the height. So we just multiply these two together, and then 1/2 times 2 is just going to be 1, so we just multiply these two together, okay, the length of these sides. So pretty simple so far. But how do we kind of find out that optimal triangle, right? We only want the maximum area. Well, we know it's pretty small, and we know a triangle has 3 points. What if we just iterate through all possible values 3 times? 100 cubed is just 10 to the 6th, and that's definitely in time. So this is going to be a valid solution. And I'll show you a little more on the whiteboard. All right, so we know kind of what our solution is going to look like and how simple it is, but first let's try to write a pseudocode for it. So first of all, we got to take in the input. And then next, what we're going to do is we're going to loop through all the points. So for I in vertices, and then for J in vertices, and finally for K in vertices, right? What we're going to do is, how do we find if it's parallel to the x-axis? Well, that would kind of look like this. And if we have it on a graph, what we can see is like, say these 2 points are here, and there's a third point here. We're considering this point, and then is this point, are these 2 points like, does the line they make parallel to the x-axis? Well, no, right? It's at this angle, right? But then this one and this one are, or they look parallel. Let's assume they are. What we can see about them is that they have the same y-axis coordinate, okay? Whereas these ones have different y-axis coordinates, okay? So that's how we do it. If, I guess, the y-axis of I is equal to y of j, and so on, right? We have a valid side. And then we also need to check if one of the sides is parallel to the y-axis. So we can do this, right? And then this is this point, and we can have this point, right? These ones are different, and these ones are the same. And what do we notice? Same x-axis. So we do the same thing, x of I equals x of j. And if that's true, then if these are both true, then what we can do is we can just take this side and this side. We can just minus the bigger x coordinate minus the smaller y coordinate, and vice versa for the y's, and multiply them together, and just store them in like an array of maxes, okay? And in this maxes, at the end, we'll just return the biggest value and return biggest to maxes. And that's it. It's like super simple algorithm that it's at its core, we're just looking through all solutions, and we have this small, like, tricky logic thing here. But even that is pretty simple, and we just have to find the maximum value. Let's code it up. All right, so we got a skeleton for the code that we're going to just implement our algorithm in. We got including bit slash std+++8, and that's basically going to include every single package we need for USACO. We also have using namespace std, which makes it just a little easier to write. And since this is an older problem, we're also going to use the file input output stuff. So this is basically saying once this code is uncommented, cin is going to be sent to from this triangles.in, and cout is going to be putting it back out to triangles.out, right? That way we can debug by commenting this and like just kind of running it in our own editor, and then we can like actually submit it just by uncommenting these lines. And since I'm just going to directly submit it, I'll uncomment them right now. Then we're taking in n, the amount of points, and then for storing points in a array, a 2D array, but it's basically just two arrays, and the 0 value is just going to be for x, and the other value is going to be for y. Another way you could do it is just have two arrays, but this kind of just cleans it up. Okay? And then now we're going to start off by just kind of having a max's value, okay? And since I don't actually know how long this is going to be, I'm just going to create it as a vector. Since not all of the points are going to have a definite like a area, because some of them we're just going to disregard. Okay? Then what we're going to be doing is we're going to do a for loop through all the values in the points array, and then just kind of do that 3 times, 3 nested for loops, so we can account for all pairs of vertices. Okay, so I'm just going to be doing a normal for loop. Okay, so I have these 3 for loops. This is kind of be like the backbone for a complete search algorithm. And one thing I want to kind of make sure is it's not really going to matter too much, but let's just have it just in case, just so we kind of get our minds thinking in that correct way. But we don't want duplicate points to be considered, right? We can't have a triangle with only one point. So what we can do is just for this j1, if j equals I, then we'll just continue, right? So that means we know j and I are not the same. And then with that knowledge, we can just do, actually that should be untabbed, if k equals I, then we can also continue. Actually, sorry, if k equals j, or k equals I. Thus, we know k is not any of those, and we can just kind of move on with that. Okay? So then, now that we have that going, all we have to do is code up the thing that checks if any 2 points are basically parallel x, and then we'll also do parallel y, and we'll store those in Boolean values. And now I just want to pause and mention that the way we're going to do this is if these are equal, then we're just going to store their values in kind of like a value, which we're going to call int y val 1 and int y val 2, and Boolean, which is going to be y works. So in all of these, we're going to set that y work, and this is going to be defaulted to false. If y works, and we're also going to replicate this for the x one. If y works or x works is either of them are false, then we're just going to instantly continue. And as you can see, I changed all the array indexes to 0 to to go to the respective x column, basically. Next, if if both x works and y works are both true, then what we're gonna do is just maxes. In maxes, we're going to do maxes dot push back abs of xval1 minus xval2, and this is just so we don't have to do any like finding which one is bigger and which one is smaller and then like subtracting it. It's just going to take the absolute value multiplied by yval1 minus yval2. And we've basically just done the majority of the algorithm. Next, what we're going to do is, since now we have this vector full of all of the possible valid triangle areas, we need to find the maximum one. So we're just going to do sorting it. And after sorting it, we're just going to see out the biggest value. So that's going to be the size minus 1 index value. And boom, we're done. Okay? So that's basically the entire algorithm. And I'll link the code down in the description. So if you want to copy it, you can. And that's pretty much it. Let's submit it and see how it goes. Alright, so editing me here, and we had a couple of issues in the code. So first of all, this right here was a 2, not a 1. So make sure to change that or it's not going to work. And probably the biggest issue is that when we were doing it, we were considering the y value points here, right? It used to be 1s, and we already know that those are equal, so we're just getting a 0 when we subtract each other. Instead, we're supposed to check the x value coordinate, so you just want to swap the 0s for 1s when it's setting the y vals, and vice versa for the x vals. Alright, so we just submitted the problem, and let's see how we do. And there you have it. So not only did this video teach you what the complete search algorithm was, but it also kind of did an example of it with the problem triangles from the USACO 2020 February Bronze contest. And remember, if you have any questions about this problem or its code or just the algorithm in general, the complete search algorithm, feel free to drop any questions in the comments. And also, to learn more and more about USACO, consider subscribing to the channel and checking out some more of our videos. So goodbye and good luck with your USACO endeavors.